Hello friends, today in this video we are going to talk about a very important topic when it comes to the competitive examination of GATE or engineering services. Basically we are going to talk about the subject manufacturing science of mechanical engineering, and in particular we are going to talk about the topic casting. So friends, I will in this video I will try to explain you various concepts of casting and how to approach a question when it comes from casting, and I will explain the various concepts involved in that question also. So here first of all, this is a question which is based on the design of pattern of mold and course. So friends, first of all I will read the question and then I will mark the very important parameters in this question, and then I will try to solve this question and also explain the concept behind this question. So the question is saying a casting of cubical shaped structure. So friends, the first data only which they have said is there is a casting which is in cubical shaped structure. And what is the required side? The required side is 60 mm. So there is a cubical casting. Let's say this is a cubical casting which is having a side of 60 mm. So this is the first important data they have given in this question. Now what further question is saying? The question is saying assume volume shrinkage of casting. So they are saying that we have to assume the volume shrinkage of casting as 2.3%. So first of all, in order to calculate the volume shrinkage of casting, we have to calculate the volume of casting. So the volume of casting denoted by VC can be written as 60 cube. Why 60 cube? Because it is cubic in structure. So the value of 60 cube will be basically 216,000 mm cube. Why mm cube? Because the dimensions are in mm, as you can see from this question. So now friends, what is volume shrinkage of casting? Basically volume shrinkage of casting is 2.3% of the volume of casting. So volume shrinkage of casting is denoted by, let's say I am denoting by VSC. It is basically 2.3% of VC. So if you will put the value and you will calculate, you will be getting the value of VSC, that is the volume of shrinkage of casting, as 4968 mm cube. So now friends, we have got the value of volume of casting and volume of shrinkage of casting. Now what the question is further saying? They are saying if the height of the side riser is 30 mm. See friends, there is again a very important data hidden in this question, that is they are mentioning it as a side riser. So friends, before coming to side risers, I will try to explain that there are basically two types of riser. The first one is top riser. What is basically a top riser? When a riser which can be of any shape, either it can be hemisphere or a cylinder or a cuboidal shape. It varies from question to question. In this question, till now they haven't mentioned that which kind of riser is this, so I am assuming it to be a cylindrical riser. So when a riser is placed on the top face of the cast, it is termed as top riser. So this is basically a top riser. And when a riser is placed on any of the sides, let's say this side or on this side or on this side, it is termed as side riser. So this is a side riser. So in this question in particularly they are talking about side riser, and what they are saying that the height of the side riser is, let's say this side riser I am writing it as SR side riser, the height is 30 mm. So the height is 30 mm. Now what they are further saying, and the riser volume desired. So the desired riser volume is 4 times the shrinkage in casting. So they are saying that the riser volume is 4 times. So basically VR is the riser volume. It is basically 4 times the shrinkage volume in casting, which is equals to 4 into 4968. So this is the riser volume. Now what they are saying in this question, they are saying then appropriate riser diameter is. So friends, till this point they haven't mentioned about the size of the riser or the shape of the riser. But if you look at the question very carefully, the side riser is having a height of 30 mm. And what other data they have given? That the appropriate riser diameter. So they are saying that the riser is having a diameter also. So if you look at the two parameters which they have given in this question, that is, one is the height and the other one is the diameter, we can straight conclude that the riser is basically cylindrical in shape, because the cylinders are only having the parameters of diameter and height. Otherwise, if you go for any other shape, let's go for sphere or for cuboid. For sphere, the only parameter is radius, and for cuboid, you have to know all the three sides value. So for this question only, the riser is cylindrical in nature, and it is not clearly mentioned. It is hidden in this question. So we can conclude that the volume of riser is basically pi by 4 d square h. Since h is given as 30 mm in this question, so we can solve, and we will get the value of diameter as 29.04 mm. So friends, if you look at the available options in this question, you will find that 29 is one of the options. But I would suggest that before concluding that 29 is the answer, you have to check the other parameters associated with design of riser. Most of you might commit mistake in the examination by taking 29 as the right answer. But 29 might be a right answer. It is not that it is the right answer. So what are the other parameters which we should check before concluding that 29 is the right answer? So I will explain it in the next slide, that if what is the basically, before concluding that, basically why risers are used in a casting. So let's say this is a casting. I am taking it to be a cubical nature only, and I will try to explain the purpose of riser through top riser. So let's say this is a top riser. So why risers are basically used in a casting? Basically the purpose of riser is to compensate the shrinkage which happens in the casting while solidification. What does it mean? It means that when the molten metal is being poured through this riser into the casting, when cooling down of metal take place, the metal in the casting starts solidifying, and as you know that metal has a tendency of contraction while cooling down. So the metal in the casting will start contracting as it cools down. So in order to compensate for that shrinkage, molten metal flows from the riser to the casting. So in order to compensate for that, the solidification time of a riser must be greater than the solidification time of casting. If the solidification time of a riser, let's see, if the solidification time of a riser is less than the solidification time of casting, what will happen? That risers will get solidified first. It will get solidified first, and the metal in the casting will remain in molten state. So what will happen when both of them will get solidified? There will be voids in the casting which won't be able to be filled by the risers. That's why the solidification time of riser must be greater than the solidification time of casting. So on what parameters does solidification time depends on? That is the next important question which comes to the mind. Basically, the solidification time of either riser or casting depends upon the two parameters, which is a ratio of V by A. What is basically V and A in this ratio? V is basically the volume of the casting. And why we are taking volume? Because volume of the casting defines the amount of heat content in the casting. And why area? Because area is the only factor through which the heat is getting dissipated into the surrounding. So this ratio plays a very important role when it comes to the calculation of time. And this ratio is sometimes being referred to as module. So this ratio is sometimes termed as module, and it is sometimes denoted by letter M. So basically what I am trying to say, that MR must be greater than or equal to MC, where R stands for riser and C stands for casting. So first of all, I will try to calculate the module of casting, which is basically V by A of casting. So what is V by A of casting? Basically, as we know that casting is cubical in nature. So the volume of casting is A cube. And what is the surface area of a cube? Basically, as you know from mathematics, that A is 6A square. Surface area of cube is 6A square. So this will and this will get cancelled and you will be getting A by 6. And in the question, it has been clearly mentioned that the required side of cube is 60 mm. So basically, it is 60 upon 6. So this is 10. So we are getting the module of casting as 10. So we will write MR is greater than equal to 10. So now we have to calculate the value of MR. Similarly, how can we write MR? MR can be written as V by A of R must be greater than equals to 10. So what is the volume of our cylindrical riser? Basically, it is pi by 4 d square into h. Since it is a side riser, so two surfaces will be involved in heat dissipation. Why so? If you look into the previous slide, for top riser which I have drawn here, one surface is basically in contact with the casting only, and this surface won't participate in any heat dissipation. That's why one cross sectional area is not considered in top riser, where in side riser we consider both the cross sectional areas. So it will be 2 into pi by 4 d square plus pi dh, which is a cross sectional area, surface area. So now it must be greater than equals to 10. So since we know that height in this question is given as 30 mm, so if you calculate it, divide and multiply by 4, pi by 4, pi by 4 will get cancelled. You put the value of h as 30, you will be getting the value of d as must be greater than equals to 120 mm. So friends, previously we have calculated that d as 29.04 mm. But if you look, this was a theoretical calculation. Now, taking into the consideration of the solidification factor of time, solidification time, we found that the d must be greater than equals to 120 mm. Since the 29.04 mm is less than 120 mm, so 29 is not the correct answer. As I have already told that 29 is a probable answer, but now we can conclude that no, 29 is not the right answer. So what is the right answer? D must be greater than equals to 120 mm. So if we look at the options available now, 15 is not greater than 120, 20 is also not greater than 120, 29 is also not greater than 120. So the right answer to this question is option D. Option D is the right answer, that is 120 mm. Now I will move to the next question. So friends, again in the previous question, since I was talking about the solidification time of a riser and the purpose of riser, this question is entirely based on the purpose of riser. As I was already explaining to you in the previous question, that the risers are basically used to compensate for the shrinkages which is happening in the casting while cooling down. So what happens now? So let's say when a metal cools down from one phase, that is from liquid phase to a solid phase, it undergoes various phases. And now I will try to explain the various phases which a metal goes through a time versus temperature curve. So let's say this is a time versus temperature curve. So on x-axis I am plotting the time axis, and on y-axis I am plotting the temperature axis. So let's say the metal is being poured at a temperature Tp. What is Tp basically? Tp is pouring temperature. So at time T1 and temperature Tp, metal is getting poured. So what happens? Metal will start getting cooled down. At what temperature, at what point till it will get cooled down? It is getting cooled down up to a temperature of Tf. And what is Tf? Basically, Tf is freezing temperature. Freezing temperature is the point up to which the metal will cool down. And what will happen at TF? At point TF, metal will start losing latent heat and it will now change its phase from liquid to solid. So let's say it is now losing its heat and now it is transforming from liquid to solid state. So basically, let's say if this is point 1 and this is point 2 and this is point 3, what happens that from point 2 to point 3, from point 2 to point 3, the metal is basically in binary phase. What is binary phase? A binary phase is a state in which metal or a material coexisted simultaneously in two phases, that is liquid as well as solid. So here the metal exists in liquid plus solid stage, and here it is entirely in liquid stage. So let's say up to time T3 it is in liquid plus solid state. As soon as it reaches the point 3, it will get converted totally from liquid to solid state. And from time 3 and temperature TF, what will happen? It will start solidifying further and it will get solidified up to the temperature TA. And what is TA? TA is basically the ambient temperature or the room temperature. It will get solidified up to that point. And from state 3 to 4, basically, what will happen? It will remain in solid stage. So if you look at the curve now properly, basically what is happening, that from temperature TP, that is a pouring temperature, to freezing temperature, the metal is in molten state or liquid state. And from temperature TF, in the temperature range TF only, from time T2 to T3, the metal which was in liquid state is releasing all its heat and getting cooled down, and it is also transforming from liquid phase to solid phase. And when it reaches point 3, it is completely transformed into the solid phase. And from 3 to 4, this solid phase of metal is now getting further cooled down to state 4, that is at the room temperature. So now friends, I will come back to the question. What the question is basically saying. Basically, the question is saying the following are the stages under which the shrinkage is taking place during casting. Okay. The number 1, shrinkage of molten metal when reducing from pouring temperature to freezing temperature. So if you look at this curve, basically what they are saying about the stage 1 to 2. Basically they are talking about this stage. Second, shrinkage of molten metal during freezing. So in this they are talking about stage 2 to 3. So they are saying 2 to 3. 3. Shrinkage of solid metal when reducing from freezing temperature to room temperature. So here they are basically talking about stage 3 to 4. So now what the question is saying, the riser in casting is provided to compensate. If you remember the previous question, I have drawn a diagram also in which I was saying that the riser was used to compensate for the shrinkage in casting, and the molten metal flows from the riser to the casting. So if in order for the metal to flow from riser to the casting, the metal must be in molten state or liquid state. So if you look at this figure, you will find that in the stages 1 to 2 and 2 to 3 only, the metal is in molten state or liquid state. So if you go to this question, that is stage 1 and stage 2 are the only two stages in which the metal is in molten state or liquid state. So the riser in the casting is provided to compensate for these shrinkages which is happening in 1 and 2. So the right answer to this question is option A, 1 and 2. Now moving to the next question. So friends, basically this is again a similar type of question as compared to the previous question, and the only difference in this question and the previous one is basically they were in the previous question asking about the riser purpose, and in this question they are asking about the shrinkage, that is solid shrinkage in a metal during the solidification is. So if you look at the previous curve which I have drawn here, you will find that solid shrinkage is happening only in from 3 to 4. And what is 3 to 4? Basically when the metal is moving from freezing temperature to ambient temperature. So now in this question, if you read the question, solid shrinkage in metal during the solidification is reduction in volume when liquid metal temperature is reduced from pouring temperature to liquidus temperature. I will once again draw the curve here so that you might not get confused. So what I have drawn in the previous slide, that on x-axis there was time and on y-axis there was temperature. So metal starts from temperature Tp, it moves to of temperature Tf. On at temperature Tf only phase transformation takes place, and it further moves to temperature Ta, that is ambient temperature. It was 1, it was 2, it was 3, and it was 4. So basically solid shrinkage is associated with this part, that is 3 to 4, as I have already explained in the previous slide also. So what they are saying, solid shrinkage in metal during the solidification is reduction in volume when liquid metal temperature is reduced from pouring temperature to liquidus temperature. Basically they are asking about this value, that is the pouring temperature to liquidus temperature. But friends, from stage 1 to 2, basically the metal is in liquid stage, it is not in solid stage. So this part is incorrect because they are asking about solid shrinkage, not liquid shrinkage. Now the second option, reduction in volume when solid metal temperature is reduced from solidus to room temperature. So basically they are saying that reduction in volume when metal temperature is reduced from solidus, so this to this. So friends, this is the correct answer, that is, so from solidus temperature to room temperature the metal is in solid state and solid shrinkage is taking place. So option B is the right answer. Now moving to the next question. So now friends, we talked about riser, the purpose of a riser, but there is one very important aspect which I have left while explaining you the concept of riser and the purpose of riser, that is the placement of riser. Where to place the riser? As I have previously drawn, if you remember, that in a cube I told you that risers can be a top riser or a side riser, but I have never mentioned that when it is a top riser, it is to be placed centrally or at the extreme corner or at this extreme corner. So basically in this question they are asking on dealing with the concept of placement of riser. So why the placement of riser plays a very important role in casting, that is one very important question which might come to your mind. See friends, what happens, let's say this is a horizontal cast, this is a horizontal cast and this is a top riser. So what happens when molten metal gets poured through this riser, it reaches to the extreme corners of the cast. Since there is a very huge temperature difference, because here the temperature is ambient, let's say Ta or room temperature, and here the temperature is something between liquidus and solidus. So what happens, that a thermal gradient exists here and heat dissipation takes place at a very fast rate, and due to this there is a end wall thermal gradient existing here at both the extreme edges, and theoretically the effect of that end wall gradient is 2.5 T, sorry, 2.5 T. So there is a 2.5 T distance where this end wall gradient phenomena is occurring. Why? Because of the temperature difference of the ambient and the molten metal. and what happens, there is again one thermal gradient occurring. And where is the, what is the phenomenon? See, as I have told you that the molten metal in the casting is solidifying at a very fast rate as compared to the riser. So the metal here is in liquid stage and here it is getting solidified. So again what happens, that there is a thermal gradient existing at this parts also, because the temperature of the liquid stage of of metal and the solid stage of metal is different. So a thermal gradient of 2T occurs here, where T stands for thickness of the cast. So basically this question deals with this concept of placement of riser only. So what this question is saying? This question is saying a 15 mm thick copper plate. So the thickness which I was talking about is 15 mm here, is to be horizontally cast, okay, with two correctly spaced top riser. See friends, this is a very important data in this question. If you miss this point, you might solve it incorrectly. So what does the term two correctly spaced top riser means? So friends, now I will draw a cast, horizontal cast with, let's say this is one top riser and this is another top riser. Now what happens, by the word two correctly spaced top riser, they are trying to say that the spacing between these two riser is such that the thermal gradient, which is 2.5T and 2T, are properly balanced. How we can do that? See friends, let this, in order to be two correctly spaced top risers, this distance must be 2T and this distance also must be 2T. Why so? If let's say they are not placed at a distance of 2t apart, that is 4t from each other, let's say the distance is something, let's say I'm denoting the distance as d, is somewhat greater than 4t, that is 2t plus 2t, there might be some places in between them where there will be no thermal gradient, and due to which casting defects will occur. So in order to avoid the problem of casting defects, the diameter for the distance must be not greater than 40. And what happens if d is less than 40? See, if d is less than 40, what will happen, that the wordings, if you see it, two correctly spaced top risers. So the risers won't be placed correctly because we are not fully utilizing the thermal gradient which is in the riser. So then the riser won't be correctly spaced. So in order for the riser to be correctly spaced, it must be 4T. So now here in this side also it is 2T. This is again 2T. This is 2.5T. And here this is 2.5T. So if you look at the length, basically they have asked the theoretical length of the bar. So if you look at the length is basically 2.5 plus 2, which is 4.5T, plus this is the dia. They have forgot to mention the diameter of the riser in this question. The diameter of the riser is 50 mm. So dia is basically 50 mm. So now 4.5T plus D plus 4T, again it is D. So D plus 4.5T. So if you will put the value of dia as 50 mm and the T, that is thickness, as 15 mm, you will be getting the value of length as 295 mm. So the right answer to this question is option B. Now friends, moving to the next question. So they basically I have talked about the design of riser, placement of riser, solidification time of riser. Now we will move from riser to another important concept of sand. What is that? That is a molding sand, which is the most important thing involved in casting. As we know that green sand mold are basically used for casting purposes. So here, while talking about green sand mold concept, there is a very important parameters. Few important parameters, or either we can say the properties of molding sand. And in this question, we are talking about one of the properties of molding sand, that is permeability. What is basically permeability? Permeability is basically the ability of the molding sand to allow the gases to escape. So ability of sand to allow gases to escape. So this is basically permeability. So permeability number plays a very important role in deciding that whether this particular type of sand can be used for casting or not. So how do we calculate permeability number? See friends, basically the calculation of permeability number is totally a theoretical concept. It has nothing to do with any nothing to do with any conceptual part. It is basically a experimental result obtained, and the only thing which we have to keep in mind while solving this question, that is we have to remember the formula, the units involved while solving this formula, while for using this formula, and the important thing is the standard sample. See friends, if you read the question is saying calculate the permeability number of sand if it takes 2 minutes to pass 2000 centimeter cube of air at a pressure of 10 gram per centimeter square through the standard sample. See, they have given the data, but they haven't mentioned that what standard sample basically looks like. What is the shape? What is the structure? How we use a standard sample in this calculation? So basically, you have to know the standard sample. What is standard sample? Basically, standard sample is a cylindrical structure in which it is having a height h and dia d, in which h is equals to diameter, which is in turn equals to 2 inches, or we can write it as 5.04 centimeter. So this is the standard sample, and you have to remember this thing, very important. Because if you don't know this part, you won't be able to solve this question. So now, what is the formula involved in calculating permeability number? It is basically pH is written as VH upon PAT. So what is V, what is H, and what is P, and what is A, and what is T? Basically, V is the volume of the air which is passing through the standard sample, and in this particular question it is 2000 centimeter cube, and the unit of the volume should be in centimeter cube. You should also have to keep a check on the units also while solving this particular question. So in this question, the volume has already been mentioned in centimeter cube, so you need not to convert it. But other way, if in a competitive examination the unit is in some other terms like mm or meter, you have to convert it into centimeter cube. Now h, basically h is this height of the specimen, and this should be also in centimeter. So in this particular question also, I have already solved it and put the value of h as 5.04 centimeter. Do take care about the units. It is very important in this question. Again, I am saying now P. P is basically the pressure at which that volume of air is getting passed, and the pressure should be in gram per centimeter square. And in this question, again they have mentioned the data in gram per centimeter square, so you need not to convert it. Area is basically the cross sectional area. It is not the surface area. it is the cross sectional area, and in this case it is pi by 4 d square, and this should be again in centimeter square. So do remember these things, very important. If you don't remember these things, you might commit a mistake. And T is basically the time which is required for that gas to pass through at that particular pressure. So it should be again in minute, and in this question they have again given it in minute. So in this question you need not convert any data, since they have already given all the data in the required format. But if the question is different, or the units are different, you have to convert it first and then put the value here. So the value pH, on putting all the data which are given here, you will get the value of pH as 25.064. So friends, this is the right answer to this question. Now moving to the next question. So now we were talking about a particular property of sand in the previous question, which was permeability. Now we will talk about another property of sand, which is refractoriness. Basically, refractoriness stands for the ability of sand to withstand very high temperature. It is ability of sand to withstand high temperature. So refractoriness of molding sand is increased with. So how can we increase the refractoriness of molding sand? Basically what they have given the option as increasing the moisture content, coarse grain size, and again they are saying that the increasing the compacting pressure and fine grain size. So if you look at the questions very carefully, basically you can also be very smart and conclude that the option, if they are giving coarse grain size and fine grain size, it means either one of them is the answer, because they are trying to confuse you. Otherwise, if the grain size, if the option is other than the grain size, they might not have given these options. So how do refractiveness vary? Basically, refractiveness depends upon the quartz content of the sand. And what is quartz? Basically, it depends upon the quartz content of sand. And basically, quartz is Si2. So there, if higher the value of quartz, that is higher the SiO2 concentrate and rougher grain size, the refractoriness would be high. So the coarse grain size basically affects the refractoriness, and it increases with coarse grain size. So the right answer to this question is option B. Now moving to the next question. So previously we are basically talking about design of molds, design of pattern, design of riser, and properties of molding sand. But from this point we will now further talking about the various types of casting. So what are the different types of casting? If you look at this question, in this question we are basically talk about 4 types of casting in list 1. See friends, basically there are not only 4 types of casting, there are many more other types of casting. In order to learn more about them, you go through the standard books, you will find various other types of casting also. So in list 1 they are saying A is sand casting, B is centrifugal casting, C is investment casting, D is die casting. And in list 2 there are various other products. So friends, if we move from list 1 to list 2, it would be a very tedious task. Why so? Because every casting method, let's say go for sand casting. Sand casting can be used to manufacture all these products, but the efficiency or the strength required or the purpose for which these products are being manufactured won't be solved alone by sand casting. So it would be better if we move from list 2 to list 1, that is which product is best suited for what particular type of casting. We will be able to solve this question easily and quickly. So in list 2, the first option is turbine blades. So what is turbine blades? basically turbine blades require very high precision casting, and turbine blades require precision. It requires very high precision casting, and it undergoes a phenomena of creep, that is very high thermal stresses are generated in turbine blades, especially in case of gas turbine. So turbine blades are basically, since it requires so high precision of manufacturing, it is manufactured through investment casting, because investment casting is the only casting method through which we can make very high precision casting products. So turbine blades are manufactured through investment casting. The second option is IC engine piston. As we are aware that machine parts or engine parts require very high strength as it undergoes repeated stresses. So since if IC engine piston requires very high strength, and for strength purposes die casting or forging is the only method which gives higher strength value. So IC engine piston is basically manufactured through die casting. Now comes large bells and pulleys. You might be getting confused that large bells and pulleys both can be manufactured through centrifugal casting. Why so? Because centrifugal casting basically is used to manufacture symmetrical products, and large bells and pulleys both are symmetrical in nature. So what happens, since centrifugal casting can be used for pulleys also and large bells also, so which one we should go for? See friends, pulleys require very high precision or axis of symmetry. Why? If the axis of symmetry of pulley is not precise, then the whole purpose of pulley will be defeated. So in order to fulfill that high precision axis of symmetry, pulleys are basically manufactured through centrifugal casting, because it gives very high precision axis of symmetry. And large mills are manufactured through sand casting. Why? Because it doesn't require that high precision axis of symmetry. So if you look at the options now, you will find that for A it is 3, for B it is 4, and for C it is 1, and for D it is 2. So option C is the right answer. Now friends, moving to the next question. So now in the previous question, I was talking more about types of casting and the casting products. But while making a cast, there are various type of casting defects which arises in the casting. So in this question, basically, we are dealing about the types of casting defects. So in list 1, there are casting defects, and in list 2, there are the remedies of that casting. So first of all, we will go one by one and we'll try to explain that how we can solve or remedy that casting defect. See friends, again I will say that these are not the only casting defects in the casting. There are various other types of casting defect also, and please go through the standard books. You will find many other more casting defects also. The only thing which I will try to explain in this video is how to approach a question of casting defect if you forgot the reasons of that casting defect or the remedy of that casting defect. If you know the phenomena that why that particular defect is occurring, you can judge from the options only that how we can remove that particular casting defect. So the first one is shrinkage cavity. As cavity word itself stand for voids or holes. So let's say cavity stand for voids, holes. So how do we remove voids and holes? So in order to get to the idea of removing voids and holes, we have to first know that why voids and holes are basically created in the first place. So let's say this is a casting, this is a riser, and this is a casting, let's say. So what happens when molten metal is getting poured through this riser? Due to not proper placement of riser, what happens that the metal which is in contact with the surfaces starts solidifying at a very faster rate due to the thermal gradient which is occurring at the surfaces. And what happens, the metal which is at the center will remain in molten state or binary phase. And what happens, Thus, since the riser is not properly placed, there are some voids are created in this casting. So how do we remove this void? Since, as you have already come to know, that due to the very fast thermal gradient existing in this casting, the phenomenon of voids is taking place. So if we provide a metal or any substance which can provide a uniform rate of cooling to this casting, this phenomena of shrinkage cavity or voids can be solved. So see, we have to provide something, as I have already explained. So if you look at the option, see, there are only options of providing vent holes. Vent holes will not affect the rate of cooling down or the rate of solidification of the metal. So the other options are providing chaplets and chills. So in order to conclude that whether the chills or the chaplets will solve our purpose, we should first know that what is chaplets and what is chills. Basically, chaplets are metal pieces which is of the same material of the casting metal, and it is used to support the core or the holes or the internal holes which we have to manufacture. So chaplets won't serve our purpose in this case. So the right answer is chills. So what is chills and how chills will solve our purpose? Basically, chills are metallic parts attached to the surface of the casting, and it is of the same metal to as to which the metal is which is getting poured here. And by providing chills, we are trying to attain a uniform rate of cooling or uniform rate of solidification. So since there would be a uniform rate of solidification, this phenomena of differential cooling or thermal gradient occurring here will be solved, and shrinkage cavity won't be taking place. So for P, the option is 5. Now, misrun. So basically what is misrun? What happens? See, let's say this is a cast and this is a riser. When molten metal is getting poured from riser, what happens that the metal before reaching to the farthest end, let's say this is the farthest end, it gets solidified. So this space remains void. This space remains void. Why so? Because metal wasn't able to reach those extreme parts and it has got solidified. So how do we remove that phenomena? We can remove that phenomena if you remember the curve which I have drawn previously in the second question, that is the temperature on y-axis and time on x-axis, that is pouring temperature, freezing temperature, and the solidification temperature. So if we increase the pouring temperature, let's say if we increase the pouring temperature, what happens? This distance and let's say this distance will be same. So what we are seeing that the time T4 is getting increased, which is T4 dash is greater than T4. So you see that on increasing the pouring temperature, we are getting more time for solidification as compared to the previous case, and this is the reason why, as I have said, that it has gotten solidified before reaching to the extreme part. So if we provide a more time for the metal to get solidified, it might be able to reach to the extreme part. So how do we solve this problem? By increasing the pouring temperature or by increasing the superheat of molten metal. So the right option is option 3. Misrun can be solved by increasing degree of superheat of molten metal. Now blister. So what is blister? Before explaining blister, I will explain you what is scab. Basically, scab and blister are related to each other. What happens if we don't provide proper vent holes in the casting? So since we are using green sand mold and it contains moisture, so when the metal is getting poured, the green sand mold gets heated and moisture will start to evaporate. And if there is no vent hole, it will try to break through the weakest portion on the casting, that a hot air will try to break through the weakest portion, and while doing so, it creates voids or holes on the surface of the casting, and these voids or holes are termed as scab. It is termed as scab, and when this scab is covered by a very thin strip of metal on the top, it is termed as blister. So as I have already told you, due to improper arrangement of vent holes, the air escaping through the molding sand try to penetrate through the top surface of the casting, and it creates a hole there. So for the, if you look at the options now, option 2, that is providing vent holes. So for blister, option 2. Now rat tail. So basically what is rat tail? Rat tail is a phenomena, let's say this is a cast, in which what happens, metal gets expanded more to in the bottom part of the casting. Why so? What happens when a molten metal is poured at a very high temperature, at a very high temperature, the sand which is in contact with the molten metal expands, and due to expansion of the sand, the molten metal at the bottom gets extra space to expand. So that extra space, when metal cools down, forms extra part of the casting. So this phenomena is termed as rat tail, and it can be avoided by avoiding the uses of wax pattern with green sand mold. So option 1 is the right answer. So if you look at the answer, 5, 3, 2, 1 is the correct order. So if you look at the options now, 5, 3, 2, 1. So option B is the right answer. Now friends, moving to the next question. So this is again basically a question which is not exactly types of casting. This is basically dealing with the types of machine molding operation. And what they are saying, in a sand slinging molding machine, the sand in the molding flask is compacted by. Basically, I will first explain that what is sand slinging molding machine. What happens in a sand slinging molding machine, in a sand slinging molding machine, let's say this is a mold, there is one pulley through which sand particles are basically getting deposited on the mold, and this pulley is rotating at a very high speed and at a very high pressure or force, I must say, that the sand is getting poured here. So now the sand in the molding flask is compacted by, the first option say, a plate that rams the sand thoroughly. So basically friends, this phenomena is squeezing. How does we say what is squeezing? Basically squeezing, in squeezing there is one ram or a plate, and this is the sand particles here, and this is moving downwards and it is trying to squeeze it. So this is basically not slant slinging, this is another machine molding operation which is termed as squeezing. So this is, sorry, this is squeezing. Now impact force by dropping the flask. So friends, impact force by dropping the flask, this is again another machine molding operation. In this what happens, that the the sand is basically getting compacted by the impact force by dropping the flask. This flask is dropped down on the table and the sand is getting compacted, and this phenomena is, again, this operation is not sand slinging, this is another operation which is termed as jolt ramming. So this is jolt ramming. So friends, this is squeezing, this is jolt ramming, and these two are both are different machine molding operations. Now the third one, combining the above two A and C. So if we combine the above, this is one A, and sorry, this is not C, this is B basically. If you combine these two also, then again this is not a sand slinging operation, as I have previously explained in this video only. So These three options are incorrect. So the right option automatically becomes option D. Throwing sand into flask with high force. As I have already told that the sand is getting thrown through this pulley at a very high force and a very high speed. So option D is the right answer. Thank you.